Hello, my name is David Betteridge and welcome to this short video on how to implement the binary search algorithm using C#. The binary search algorithm is a classic computer science algorithm and one, if you're new to programming, I would thoroughly recommend you try and implement yourselves after watching this video. In the first part of this video, I'll describe what the algorithm is and why you might want to use it. Then in the second part, I'll demonstrate how to implement it using C#. The basic implementation will be the same in any programming language. And then in the final part of the video, I will use some of the more advanced C# features to make our implementation a bit more reusable. So what is the binary search algorithm, and why might we use it? Imagine you have a list of items which are already in order. So in this case, we've got a list of words which are sorted into alphabetical order. And you want to find out whether or not a word is in the list. And if it is in the list, whereabouts in the list it is. So for example, if you wanted to find if the word elephant was in the list, you'd probably start at the beginning and you'd look in the first location, it's not there, the second, the third, and so on, until either you got to the word elephant, or you got to a word that comes after elephant in the alphabet, in which case you know you can stop looking. So for example, if you wanted to see if the word zebra was in the list, you start at the beginning and you check each of these locations until, in this case, we actually ran out of entries in the list, so we know zebra's not in the list. So this is fine if the list is quite small, because it won't take too long just to search all the way through, especially in this case where we only have 9 items. But imagine the list is much bigger, say 10,000, 100,000 or even 1,000,000 items, in which case searching for 1,000,000 items could be quite time consuming, and especially if you need to do it multiple times in your program. Binary search is a way of speeding up this process. One thing to remember about binary search is that the list must already be sorted into order. So in our case we've sorted our words into alphabetical order, but if it's a list of numbers you'd already sort them into numeric order. To use the binary search algorithm we have to work out a couple of things. First of all, we need to work out where the start of our list is, so here in this case. And also work out where the end of the list is, here. And once we've got the start and the finish, we can calculate the middle. And the rule for calculating the middle is you add together the start location, the final location, and you divide by 2. So in this case, 0 plus 8, which is 8, divided by 2, which is 4. So the middle is 4. Let's say we're searching for the word elephant. We then compare elephant with the location, with the word in our middle location. So we compare elephant with dog. Now we know that dog comes before elephant in the alphabet. So that means we can actually discard everything in this half of our list. Because we know elephant's after dog in the alphabet, there's no way it can be in this half of the list, so we can discard all of these. And once we've done that, we can then repeat the process. So now the start of our list is elephant, because we've already discarded everything to our left. And the end of our list is still house, and again we calculate the middle. So this time it's 5 plus 8, which is 13, divided by 2, which is 6.5, and we always round down, so the middle now becomes food. We now compare elephant with food. Well, food comes after elephant in the alphabet, so this time we can discard everything to the right of food. And then we do the process once more. So now our start pointer is still on elephant. The final one is now on, is also on elephant, and so the middle's on elephant. And when we check, we've actually found elephant. So we know that we found the word in our list. Let's try another example. This time we'll try searching for zebra in the list. So as before, we know the start and the finish, and we can calculate the middle, which is dog. We can check, and zebra comes after dog in the alphabet, so we can discard everything on this half. We then repeat the process, elephant, house, and food. So we compare zebra with food. Well, zebra comes after food in the alphabet, so we can discard everything here. We continue the process again. This time the start is garden, the finish is house. The middle point is garden, because it's 7 plus 8 divided by 2, rounded down, is garden. And again, zebra comes after garden in the alphabet. And then finally we get to a point where the start and finish pointers are at the same place, they're both at house, and that doesn't contain the word zebra, so we know that zebra isn't in our list. So hopefully you can see that as before, before we started at the beginning of the list, in order to check zebra was there, we had to do 9 comparisons. So this time we've only had to do 1, 2, 3, 4 comparisons. So it's already quicker and a lot less work to do. The question is, how much quicker is it? We know that if our list was 1 million items long and we had to search through all of them, then we'd have to look at 1 million entries. So how many entries would we have to look at when we're using the binary search algorithm? Well, the way to think about the binary search algorithm is every time we're dividing the list in half. So we'll make the maths a bit easier, but let's say we started off with a list with 8 entries in it. And then we divide that in half because it's either going to be in the left half or in the right half. So then we end up with 2 smaller lists of 4 entries each. And then we divide those up into 2 because we're always discarding half of the entries each time. And then we go again until we end up with entries which only contain 1 item each. You'll have to excuse my drawings. And then the number of comparisons we've done is then the height of this tree. So in this case the tree is 4 high. So the most we need to check would only be 4, because each time we're halving the list. And so the way we can calculate from, if we know the size of the list, how many comparisons we need to do, is now going to be the log base 2. So the log base 2 of 1 million is about 20, so we'd have to do 20 comparisons if our list was 1 million items long. But 20 comparisons, as you can see, is a lot less than scanning through 1 million items. I'm now going to create a basic implementation of this algorithm using C#. To get started, I've created a brand new console application in Visual Studio. So the first thing is we need some items to search through. So to begin with, to make things easier, I'm going to have a list of numbers rather than words. So we're actually going to have an array, and we should have some numbers. And remember, they must already be sorted into order, so numeric order in this case. It doesn't really matter what the numbers are. Testing. And then we can have a function called search, and we're going to give it our array of items and the one we want to find. So let's start off with trying to see if we've got 60 in our list. And that's going to return the location of it in the list. So in this case we'd expect it to return 2, so as it's in the 3rd position, and we start counting from 0. So we just write that to the screen. So let's say 60 was found at position 0. And we'll have a couple more examples. So we'll also search for 10,000. So that's going to be 0, 1, 2, 3. Oh, I've done that wrong, haven't I? 0, 1, 2. Sorry, that should actually be found at position 2. 3, 4, 5, 6. So that's going to be 6. And then we'll also want a couple of examples where the item isn't in the list. So for example, 45 is not in the list, so we need to work out how we're going to represent things not being in the list. So we have a few options. Our search function could throw an exception if the item is not found. And that's a valid thing to do. If you know that the item should always be, the thing you're looking for is always in your array of items, then it really is an exception if it's not there, and so throwing an exception would be fine in that case. If you're not sure whether the item is going to be in the list or not, then throwing an exception normally isn't the best thing to do. So we can either return a Boolean variable using a reference argument, or we can return a negative value for index to specify that it's not in the list. So that's like when you use the index of on a string and there's no match, it returns -1. So that's what we're going to do in this position, in this case. So we'd expect this to return -1. And then finally we'll do a test for items, again not in the list, but actually comes off the end here. So that's the one. So now we need to implement our search function. So our search function takes into argument the array of sorted items and the item to find. And it's going to return its index of its location, or -1 if we haven't found it. So as we were doing in the diagram, we need to work out two things. We need to work out where the left is. Well, the left hand side is always going to be the first item, and the right pointer, which is always going to be the final item in our array. So we take its length and subtract 1. Now we can calculate where the middle is. So the middle is, as we saw before, it's the left plus the right divided by 2. Because this doesn't return an integer, we're going to have to round that down. So we always round down, so we use the maths.floor function. And the problem is we now get a compile error. And the reason is because we've got a mixture of data types here. We've got a result which is a decimal, but we're dividing by an integer, so we just need to change the types. And then our result is still coming back as a double, so we just need to cast that to an integer as well. So now we can start checking to see what element we have in the middle. So we can say if the item we want to find is in the middle, then we're done, and we can just return. We can just return the location of the middle. If, however, the item we want to find is in the second half of the list, then we can move our left-hand pointer to be the old middle location plus 1. And then finally, which we need to do an else or an else if for this one, if the item we want to find is in the first half of the list, we can then move the right pointer to the middle -1. And we keep doing this until either we find the item we're looking for, or we get to a point where the two pointers have crossed over, the left and the right pointer, in which case we have to exit. So we need to do a check for that. So we're only going to do our loop whilst they haven't crossed over. So whilst the left is less than or equal to the right, we can keep going. And once we get to the point where the right comes before the left, we know the pointers are crossed over and our entry definitely can't be in the list, so we need to exit. And we return -1 at this point to show it's not in the list. So let's put a breakpoint here and try running our program. And we've got the results we were expecting. So we can quite happily search for integers in our list. We're now going to look at a more advanced implementation for our search algorithm to make it a bit more reusable. So the solution we've come up with at present works fine, and it will quite happily do a search against sorted arrays of numbers. But what would happen if instead of numbers we had a sorted array of words, such as the words we were looking at earlier? So let's try using that with our algorithm. So instead of passing our items, we're passing words, and this time let's say we're going to look for bear. And we'd hope that bear would return in location 1. Just possibly made a mistake there, so I shall fix that as well. And as we can see, this doesn't compile. And the reason it doesn't compile is because our function is expecting integers to be passed in. And obviously we could change our function to accept strings, which would fix the problem, but then break it for all our previous cases. So what we need to do is we need to find a data type that allows us to pass in both integers and strings. So one idea is you could use objects, but it won't quite compile as it is, and even if it did compile, it still wouldn't quite be correct, because there's nothing to stop you passing in a list of numbers but then trying to find a string in that list, and that doesn't really make sense. So what we need is a way of restricting these types, and the way you can do that in C# is to use something called generics. So what we say is this function has a generic type, which means it can be any type with some restrictions, and we're going to say that our array contains these types, and the thing we want to find is also of this type. So now when we call it from this function, t is equivalent to an integer, so we've got an array of integers and we're trying to find an integer, and when it's called from this function, t is a string, so we have an array of strings and we're trying to find a string. However, it still doesn't compile, as we can see here, because C# doesn't understand how to compare objects of type t. So t might not be a string and it might not be a number, it could be like a person class, for example, in which case what does it mean to say is one person class greater than another person class? So we need to restrict our t's further, and we can do that by adding a where statement here, and we say where t, in this case, has to implement an interface called iComparable, which means objects of this type can be compared. However, as you can see, it's still not compiling because it doesn't understand the less than and the equal symbols. So instead you have to use a function called compare_to. So the way that works is you take the first value, you call compare_to, and you pass it the second value. Compare will return one of three values. If it returns the value of 0, it means it's a match. So item defined is the same as item's middle. So we can say that equals 0. If, however, items defined is after item's middle, the middle item, then it returns a value of 1. And finally, if the item we're looking for is before the middle point, it returns a value of -1. So we can see it now all compiles, so let's try running it. And now that's working, and it's correctly found bear is at position 1, which is what we expect, and also all the previous examples are still working. So that's quite good. So we can now search against any sorted array. However, what would happen that instead of using an array, we decided to use a list. So in this case, it can be a list of strings. So we'll pass in the list instead of the array this time. And let's search for carrot. And carrot's going to be 0, 1, 2, 3, position 3. So as you can see, again, it's not compiling because our function is expecting an array of type t, so an array of strings in this case, and we're trying to pass it a list. So what we need to do is, instead of passing it an array, we need to pass it something else. So we can't just pass in object, because if we just passed in something of type object, it wouldn't understand what length meant, and it wouldn't understand that you can index into it, like an array or a list. So what we need to do is find a data type that's common to both arrays and lists, which gives us both a length and a way of accessing individual elements. And the data type or the interface we need, in this case, it's called iList. So as you can see, it doesn't compile because iList doesn't have a length, but it does, however, have a count method. And it also has our indexer on there. So it now compiles because both a list and an array are of type iList. So let's run this again, and we'll just make sure it works for our new example. And that's looking good. So just to summarise, in this video we looked at what the binary search algorithm is and why you might use it, and why it's so much quicker than having just a long list. So you can work out roughly how many comparisons by using the log function. We then implemented a basic version using C# that just allows us to search for items in a sorted list of numbers. And then in the final part of the video, we extended it so we can search for against sorted lists of any type, and they can either be arrays or lists. Hopefully you found that useful, and we'll try and implement it yourselves. Thank you for watching.